The three-body problem asks, given three objects in space exerting gravity on each other, can we predict their motions? On its face, it seems simple. Newton's laws predict two bodies will orbit in nice ellipses. But as one dynamicist quips, it became the first real worry of Newton. In practice, two masses orbiting each other are easy to solve, but add a third, and the motion can become wildly complex. Tiny changes in a body's starting position or velocity can send the system off on a completely different trajectory. It's like walking on a mountain range. A nudge left or right leads to very different fates. In most three-body scenarios, there simply aren't enough constraints to write one neat equation for all cases. The roots of this problem go back to Newton's principle in 1687. Newton solved the two-body case like Earth and Moon, but noted that adding the Sun into the picture made predicting the Moon's motion extremely tricky. Over the next century, mathematicians chipped away at special cases. In 1767, Euler found solutions where all three bodies lie on a line. In 1772, Joseph Louis Lagrange discovered a family of equilateral triangle solutions. In Lagrange's configuration, the three masses always form the vertex of a rigid triangle, moving on Keplerian ellipses. These special orbits, forming two stable L4 and L5 points among 5 total Lagrange points, are valid no matter the mass ratio. However, as modern researchers know, these elegant solutions are exceptions. There are solutions for special cases. One mathematician explains, but there is not a simple formula to give you a general solution. Lagrange points and spacecraft. Remarkably, those Lagrange solutions have practical use today. The 5 equilibrium points in a two-body system are where a small object feels balance, gravity, and centrifugal forces. NASA missions exploit them. For example, the James Webb Space Telescope orbits near the Earth's Sun L2 point, staying in constant sunlight and line of sight to Earth. The upcoming Lucy mission will travel to Jupiter's L4 and L5 points to study the Trojan asteroids caught there, because objects in these orbits require very little fuel to hang in place. They are ideal for telescopes and probes. Poincaré and chaos. In the late 19th century, Henry Poincaré proved a sobering fact. The general three-body problem cannot be solved with a single formula. He showed that for almost all initial setups, the system is chaotic. Tiny perturbations grow exponentially, making long-term prediction impossible. In other words, even though Newton's laws still apply, the resulting motion is so sensitive that no closed-form solution exists. This deep result means physicists must usually resort to other methods when faced with three interacting bodies. Numerical and modern approaches. Lacking a general formula, scientists turn to numerical simulations, using powerful computers and step-by-step integration. We can predict three-body motions to high precision. In fact, modern research has even cataloged vast numbers of special cases. In 2000, mathematicians Chensener and Montgomery proved that three equal masses can eternally chase one another in a beautiful figure-8 orbit. More recently, teams running supercomputers searches have identified thousands of new periodic three-body trajectories. These orbits twist and loop in intricate ways, like lacework in space. Chaotic behaviors and resonances. When the intrications are generic, the behavior can be baffling. In many three-body encounters, two bodies collide or one is flung away as a rogue planet. In fact, studies estimate there may be 20 times more free-floating planets than stars in our galaxy, many born from three-body ejections. Yet, in some systems, resonances impart stability. For example, in a binary star system, a planet orbiting far from the pair effectively sees them as one big star. Such circumbinary planets can have nearly regular orbits. Similarly, mean motions resonances like objects in step. Pluto orbits the Sun in a 3-to-2 resonance with Neptune, a heading three-body interplay, and Jupiter's Trojan asteroids share its orbit at L4 and L5 points. These counterintuitive arrangements, from Trojan swarms to co-orbiting moons, illustrate that some special three-body configurations can be surprisingly steady. Real-world implications. The three-body problem touches many areas of astronomy and spaceflight. For space missions, it guides trajectory design. NASA's SOHO Solar Observatory sits at the Sun-Earth L1 point. Gaia and GWST orbit near L2. And even lunar transfers use multi-body gravity assists. In planetary science, it influences stability in triple star systems and multi-planet systems. For example, a recent astronomical study reported evidence for a supermassive triple black hole system locked in a complex waltz before merging, a cosmic scale three-body dance in popular science. The problem has even captured imaginations. Lou Sexton's novel The Three-Body Problem, Hugo Award-winning, dramatizes the chaotic orbits of three suns, though such a system would likely be inhospitable to life. More broadly, research into the three-body problem has driven advances in mathematics and physics. The quest to understand it spurred chaos theory, numerical methods, and new mathematics. As mathematician Richard Montgomery notes, tackling this problem adds to the work of people like Newton, Poincaré, and Lagrange. Even without a one-size-fits-all answer, studying the three-body problem has yielded insights, from designing space missions to understanding planet formation that ripple through science. The three-body problem may never have a simple closed-form solution, but its unraveling continues to illuminate the cosmos. By combining clever mathematics with computer simulations, we peel back layers of this cosmic mystery. In the end, the unpredictable dance of three gravitating bodies remains both a challenging and an inspiration, a reminder of the rich complexity of the universe. Thank you for watching. See you next time.